Yeah, so speaker at this point is Owen. Thank you.
Okay, so we just recap sort of the highlights of what we did last time. So we had some mechanical system. Which I sort of asserted should be encoded by a Poisson map. We talked about three types of symmetry in sort of two directions. So the classical level, there was a group level of symmetry. So we had some maybe Lie group mapping. I talked about diffeomorphisms, but I want to shift that to being a common arena. So if you have a diffeomorphism, it acts on functions by pullback. So it induces automorphism of the algebra of functions. An automorphism has a commutative algebra. It's just pulling back the map of commutative algebras for each element. We had a Lie algebra level. So the Lie algebra, or the Lie algebra map to derivations as a commutative algebra of C infinity of F. So far, these just involve the smooth action of a Lie group on a manifold. But because we have a Poisson manifold, you can ask for something more. And so we talked about this notion of a moment map.
Sorry, should those really be seen as derivations?
Absolutely. I mean, that's a sub, right? It's okay. So this maps to C infinity of n. There's some Poisson map. And these two levels, these Lie algebraic levels, were related. So there's obviously an inclusion of G into polynomials in G. That's what sim G means. And we had this Hamiltonian map. So if I had some function in here, it went to the derivation, which was the Poisson bracket. Okay. So that was the classical level. We called this level, by the way, just to remind you of the moment map, or what moment map does the level of function. There was also a quantum level, where by quantum chose to focus on the notion of deformation quantization. So over here we had C infinity of m as a Poisson algebra. Over here we maybe fixed a deformation quantization. So this is an associative algebra over our series in H bar. So instead of thinking about G acting by automorphisms as a commutative algebra, we think about G. We would like G to act as automorphisms of an associative algebra for power series in H bar. I'm going to be lazy. I'm going to call this AQ. I don't have to keep writing. So I guess this would be a classical. An ideal case, G maps to derivations as an associative algebra of the quantization. And then we had this deformation quantization of polynomials in G, this H bar weighted version of the universal enveloping algebra. And we ask that this be a map of associative algebras. So this was Poisson algebra. Now this is an associative algebra map. We still have an inclusion here. This is actually a map of Lie algebras. And we still have a version of a Hamiltonian map. If you have an operator here, F, in instead of going to the Poisson bracket, it goes to the commutator bracket. With respect to this. Two stories should be related. I don't know why I like using color so much. Okay. Doing things mod H bar. So the dequantizing direction. Quantization is not really meaningful, but dequantization is meaningful in some sort of like broad makes sense. So Pablo pointed out that I didn't give any examples of one of these quantum moment maps. So I'm going to give an example really quick, so it doesn't seem totally empty. So give me an example. Quantum moment map. So we talked yesterday about the example of the cotangent bundle of R3. I'm going to tell you a modest lie, but I think it's okay. So this has an action of the translation group and the translation of the algebra. The deformation quantization I want to use is going to be differential operators, the ring of differential operators on R3. So this means differential operators. And I claim there's a map from UG. So I've just set H bar to 1 here, just out of laziness. Now G here is just generated by d by dx1, d by dx2, and d by dx3, the infinitesimal translations. So I'm just going to tell you where these things go. D by dxj maps to d by dxj. This is my quantum moment. Okay. These are differential operators. Right? And you can imagine if we replaced R3 by SO3 to the translation case, this becomes little SO3. I'm going to write a basis for this thing. But if you get the usual, you can talk about differential operators on SO3. You get the usual sort of differential operators that have to do with infinitesimal rotation. Those are example. That's another example of a quantum. Okay, so we have this really nice story about symmetry, and the goal of the rest of the lectures is to try to articulate some analog for field theories and not just mechanics. So part of what we need to do is say what are the replacements in a field theory for talking about, say, a Poisson algebra or an associative algebra. So I'm going to start by giving you a definition that will end up providing a kind of answer. So I'm going to get out of the way the sort of slog of getting through a definition, and then we'll get to the explanation of why it's a kind of answer afterwards. It's a very math kind of approach to emphasize definitions first. Save a little space over here for an example, running example. Refactorization algebra is what I'm defining F on a manifold M with values in a symmetric monoidal category, I'll write like this. Consists of the following data. So I'm going to stop here for a moment because I'm not sure everyone knows what a symmetric monoidal category is. I'll very briefly indicate what kind of thing it is without spelling out all the axioms. So a monoidal category. Notice the word monoid here, some kind of multiplication. Means a category where you have a way to maybe combine or multiply objects and maps in the category. So I'm going to write examples that I hope will give you the flavor of what's going on. So you could think about the category of vector spaces over some field K. And there's some way of making new vector spaces by taking tensor product over that. Right, so the tensor product is the way of multiplying objects, and you can tensor maps too. So over here, when I write C, upper tensor, C is the category, and the tensor is some symbol for the way to combine objects. Another example, though, with the same category is to take direct sum. That's another way of combining vector spaces to get to vector spaces. There are nonlinear examples, like you could think about the category of sets. One way to put sets together is to take their Cartesian product. You could think about sets with disjoint unions. And there's lots of variations on this kind of thing. So we can think about topological spaces with the product, topological spaces with disjoint union. We could go kind of in the homological direction. We could think about chain complexes over a ring K. We could take tensoring over K. Or we could again take chain complexes, work with direct sum. There's lots more examples, but I think hopefully from these examples, you can think this is not some crazy abstract notion. I've spent a lot of time working with tensoring of or adding direct summing vector spaces. So the way of putting them together is the monoidal structure. Being symmetric monoidal means this operation is essentially commutative. If I put A with B, there's isomorphism to putting B with A. Okay. Questions? Each open set U and M, I have some object F of U in the category C. So maybe let me start my examples just so this doesn't sense. So what I'd like to explain here as a running example is how an associative algebra A, so that's some vector space with some way of multiplying objects, determines one of these factorization algebras on R with values in vector tensor. So, and here's the real line. Category is vector spaces with tensor product. So here's my picture of R, my manifold. If I think about the open, say the interval I, it's open interval I, what do you think? We call this thing some fancy A. What do you think A of I should be? What vector space should A of the interval be? In the vector space, what vector space do I have at hand? A. A, very good. So this is the underlying vector space. Okay. So we know this. So for each finite collection, U1, U2, UK, of pairwise disjoint opens. An open set V containing Uj for all J. Okay. Map f of U1 tensor f of U2 f of UK f of. So if you want, there's some way of kind of multiplying things that sit on each of these opens to get something that sits on the big open. So let's do that over here. So first of all, let's do the case k equals 1, a unary operation. So here I have the real line. Suppose I pick, so here I have I again. So I'm just having it float, so I have a little bit of, but it's, you should think about it as an open down here. I'm just kind of labeling it sort of being included. Maybe it's sitting inside of some bigger open J. Okay, so I have A of I. I want to map to A of J. Remember, this is the vector space A. It's also the vector space A. What do you think the map is? Identity. Identity. Very good. Okay. So far, so good. We said we did with one. Yeah, question? Is this supposed to be connected? Doesn't need to be. Okay, let's do the case k equals 2. Okay, so here we have the real line. And now let's imagine I have, yes, I1, I2. Those are disjoint, right? Sitting inside a some big J. I'm supposed to have a map from, well, A of I1 tensor A of I2, which is just A tensor A. This is supposed to map to A of J. Well, that's A. What am I supposed to do? Thank you. Okay. So you could think about there's some element A1 sitting on here and A2. And where does it go in here? It just goes to A1 times A2. And I'm multiplying A1 by A2, just in the order on the line. Okay, so this is multiplication. And in general, if you have a bunch of intervals that are disjoint, you just do the multiplication from left to right like you do in associative algebra. And that's what these maps are supposed to be. Okay, so this was the data. Satisfying the following conditions. So I don't want to write them out technically, mostly because it becomes a little bit long-winded. I think it's just as easy and clear to explain by an example. So it's going to satisfy a kind of associativity condition. Okay, so I'm going to draw a picture. So suppose I have some big open set W. Inside it, I have U1, U2, U3, U4, U5. I may regret trying so many things. There's some bigger open V1, U2. Well, so these U's sit inside of W. So there's a map, thanks to my axiom, to F of W. But there's also a map from F of U1 tensor F of U2 to F of V1. There's a map from F of U3 tensor F of U4 tensor F of U5 f of v2. And of course, there's a map from these things up to here. I would like this to compute. Okay, so more generally, if you have sort of, a bunch of opens, including into a set of opens, and you go further, it has to commute in this way. So let's see why I called it associativity. Let's do our example. So imagine I have intervals I, J, a little more space. I, J, K, moving into some big interval L. Well, each of these intervals gives me a copy of A. So I get A, tensor A, tensor A. This is a single interval. And so I'm going to send A tensor B tensor C in here. Get A times B times C. But we could factor the inclusion of these three intervals into L in some way. Like for instance, we could put I and J into M and N, right? And here there's a map. So over here, we have a copy of A tensor A. This thing goes to A times B, right? I'm multiplying A and B here to get something in here. Tensor C, and then I multiply what's on here with this element here. Okay. But we could also have factored it like this. What comes after? Okay, O, P or whatever. So we also have this map, A tensor A to here. This goes to A tensor B dot C. And either way of including three things, factoring three intervals into a big interval, has to give you the same answer. So we know that there's no ambiguity. We can parenthesize any way we want. Okay. Other condition is equivariance under new labeling. So over here, the way I wrote it, I imagined, I ended up putting an order in. If you want, I have U1, U2 up to UK. And don't think about that as being sort of intrinsic information. So let me explain what I mean by that. Suppose again, I have some big open, say V. I have two opens inside of it. I could choose to call this, say, U1 and U2. So I get a map from F of U1 tensor F of U2 to F of V. But maybe you chose to label this as U1 twiddle and U2 twiddle. They're just labels, right? So I also have F of U1 twiddle tensor F of U2 twiddle. And there's a multiplication here. Now these two tensor products are isomorphic just by swapping, right? So this tensor factor is isomorphic to that tensor factor. This factor is isomorphic to that. So there's a swap map. It's an isomorphism. And I want this diagram to commute. Okay. Yeah.
Does that mean you want your associative algebra to be a commutative algebra?
Nope. Okay. So Another way of saying it is once I tell you what the map is for some choice of labeling, I know what it is for everything else just by using the swap map to work out what it is.
Can you explain the nuance of how this is different than the symmetric structure? Wasn't the symmetric that you could change the order of operations of type?
It's just isomorphism between tensoring objects. So the existence of this map is from the symmetric monoidal structure.
Okay.
But this has nothing to do with the symmetric monoidal structure. This is data of the refactorization algebras. Good question.
But it would be enough to have a monoidal structure, right? Symmetric is not really used.
In the 1D case, you could get away with monoidal, but in the higher dimensional case, you need symmetric monoidal to do this. There's a variant of these things, which if you're thinking about one-dimensional manifolds, you don't need a symmetric monoidal category, you just need a E1 monoidal category.
Sorry, I'm confused. Could you explain again why your algebra wouldn't be commutative? But
How about that's an exercise you sort out for yourself? It's some sort of remarks. So first off, with this running example, we saw that you could encode an associative algebra as a prefactorization algebra on the real line. So the examples we saw yesterday all involved things that were, among other things, associative algebras, the examples of the moment maps. So since associative algebras give prefactorization algebras on R, the quantum moment maps determine maps of prefactorization algebras. So it's certainly a home where we can re-articulate the structure that I talked about. Yeah.
Sorry, so this diagram requires this symmetric condition, so the braiding is not sufficient?
It would be sufficient in 3 dimensions and lower. Could we not dwell on this point? This is like a really subtle wrinkle on this definition. And I think if you want to talk about it, I'd be happy to talk about it.
Yeah, like it's just a symmetric monoidal function, right? Is a prefactorization.
You could articulate this. Can we get that remark in just a second?
Okay.
It's not always true. I mean, well. Okay. The point I want to say here is just that the story we told fits inside of this world. It's a world big enough to accommodate what we've already talked about. Another remark is that if you draw the 2D pictures, kind of like I've been doing here, they probably look familiar. But different people will see different familiar things in them. So a physicist, so the kind of picture I have in mind here is you have 2 disks inside of a bigger disk. A physicist might see sort of the OPE, operator product expansion, in a conformal field. You have a operator here, it gives you an operator here. A topologist sees they give an E2 algebra, an algebra over little 2 disks off of that. And a theist, he sees a pair of pants. This is a squashed, flat pair of pants. If you have a pair of pants, you were looking at it from above, looking into your pants before you step into them, you see this. Maybe if you have leggings or something, these will tighten up as you go down. So this is some foreshadowing of how prefactorization algebras show up in other areas. So show up in these areas. I had one more remark. Turn into Connor's comment, which is you can describe this notion very efficiently using the language of colored operands or multi-categories, if you know that language. Okay. Or as I think Connor had in mind, you can take this symmetric modal envelope of the colored operand and then some symmetric modal function. With some algebra over a colored operand. That's particularly useful if you want to sort of do, you know, a modern thing and homotopy coherence here rather than like some sort of strict notation.
Category of events and.
Yeah, if you take the symmetric modal category under disjoint union, yeah, that's exactly right. There's a, yeah. Maybe better is there's a colored operand of opens, and its symmetric modal envelope is some nice symmetric modal category. So that's do what you want. Okay. So we now have this definition, prefactorization algebras. I've shown that at least in the mechanics case, you could, if you wanted to, rephrase that stuff in terms of prefactorization algebras. I'd like to explain maybe a raw kind of schematic of why it should show up more generally in field theory. So thankfully, Conrad more or less gave the warm up for this. So I'm going to be a little bit hopefully at least some of these terms feel somewhat meaningful when I get started. So let's start with classical field theory. So as Constantine said, classical field theory say T lives on some manifold M with fields F being sections of some fiber bundle over F. Think about the trivial fiber bundle if you want to think about smooth functions. And then there's another bit of data, important data. And there is the sort of crucial bit about the there's a PDE, which have been called the equations of motion. Which picks out inside of the fields some locus. These are the fields where it satisfies, say, the P. Okay, so P is just some shorthand for that. For the dimensional equation. So we've actually met or sort of gestured at an example. So mechanics has M equal to the real line. The fields might be smooth maps from the real line into some target space X, like we talked about R3 or SO3. And then our PDE, in this case, is the ODE we talked about before, which would be the So here, inside of here might be some, we wrote it as x of t yesterday. T is the time parameter on the real line. So the second derivative of x is some function of time, position, and velocity. Yeah,
What inside that set, what is F?
that's the solutions.
Little F.
Where, here?
No, right?
That should be a 5. Thank you.
Okay.
It's a condition on 5. Okay, thank you.
Let's say I call them Lagrange equations.
Yeah, I did have that in my notes, and I forgot to, so. I find EL kind of a hard mnemonic, so. This is Constantine's Euler-Lagrange. He's emphasizing the equation, and I'm just saying, solutions. This is the dictionary. Thank you. Let me rephrase what's going on with this structure a little bit in a way. So there's a category that I'll call open M. It's a category. An object is an open subset. U inside of M. And a morphism is just given by inclusion. So U and V are both open sets. And they say there's a map from U to V if U is contained in. So this is actually the category determined by the post set of opens, post category. Okay. In fact, there's 2 functors. So first off, there's a functor I'll call F. It'll be a category of spaces that I want to postpone talking about. So what does F do? F of U, well, it's just going to be sections over U of the fiber bundle restricted to. It's just the fields on the open set. Okay, so there's a nice functor that actually goes to spaces off. And why is that? Well, if U is contained in V, well, I also have F of V, that's sections of F restricted to V over V. If I have a section over V, since U sits inside of it, I can pull back sections and have a restriction. So it flips the direction of the morphisms. So it goes from opens to spaces off. So I need spaces to be a category that contains whatever F of U is. So, if I'm thinking about smooth sections of some vector bundle, spaces has to include these sort of infinite dimensional vector spaces. Questions about this so far?
Why didn't you put the op on the other side?
Because there's gonna be another functor that's contravariant, and it's convenient to do it this way. But you can do either way. And I know you're not used to having an op over here. There's another functor here, which is solutions. So the nice thing about a PDE is that is very nearly a pointwise condition. It's a local condition. The condition that only depends on the Taylor expansion of a function at each point. Okay? So in fact, inside of here, we have solutions on U. We have solutions on V. If I satisfy a differential equation on a big open, it restricts to a solution on a small open. So in fact, we have a natural transformation this way between solutions and all the fields. Questions so far? So there's one more functor I want to talk about. the category of commutative algebras. If I have a space, I can talk about the ring of functions on that space. So depending on who you are, we might call this C infinity, maybe curly O. So let's just be optimistic and imagine this collection of spaces does have a ring of functions. So we have a composite functor, and this is also contravariant. So this is good. Let's,
So those are the observables?
yes. So let the classical observables be this composite functor. Okay, so that this is a functor from opens on M. It's a covariant functor. The commutative algebras. I have, since I have this, say, mapped this way, if I have a function on the solutions on the small open set U, it pulls back to a function on the big open set B. Okay, so claim, so these are the observables, the classical observables. The claim is that obs, classical, is a prefactorization. Let me sketch why. So suppose I have an open set U1 and an open set U2. They're contained some big open set. Well, solutions on U1 disjoint union U2 amounts to getting a solution on U1 and a solution on U2. So this is naturally isomorphic to solution on U1 plus solutions on U2. We've already talked about there being a restriction map from solutions on B. So there's also a map like this. So now we take C infinity of so this is a slight lie, but this is smooth functions and solutions on U1. Tensor C infinity solutions on U2. Maybe I should just not lie. There's certainly a map this way. In good cases, you complete the tensor product. We also have this map here. Functions on solutions on B. And this composite is the structure map of the prefactorization. It tells me how to combine an observable living on U1 and an observable living on U2 to get an observable on the bigger open B. So I could write this if you want. Right, this is obs classical on U1, tensor obs classical on U2. This is obs classical on B, and I've just given the map that I need. Once you understand how to do the 2-to-1 map, you can do any finite collection. It's the same argument. Okay. So this is the broad conceptual reason why observables of a classical field theory always form a prefactorization algebra. Now, to actually do it carefully, to do it like a mathematician, you have to pin down this category and this functor. Okay, So one way of doing that, Constantine's been laying out, for instance, one way of approaching that. BV does that by describing these spaces as some version of DG or derived manifolds. Now you took the space of all fields and equipped with a cohomological vector field. And then you could think about that if you want as a kind of resolution of the space of solutions. And then he wrote down an EG algebra, which is the ring of functions on that derived manifold. And that's a kind of resolution of the naive space of solutions. Okay, so the BV formalism is some kind of homological thickening, a sort of naive idea. So I should say that trying to actually make this work. So in the perturbative case, you can be very precise about this. It's just a side comment. But in the non-perturbative case, this is like work in progress of several different people. The state of the art right now might be some recent work of Paula Steffens. Be happy to tell you what I understand of that in conversation. Okay, so I'm not going to pursue that right now. What I'd like to do, and just giving you a sense of why observable should be a prefactorization algebra. I'd like to go and talk about symmetry algebras, right? We talked about there were two sides of this discussion. There was sort of the observables on the field theory, and there was supposed to be the symmetry algebra, so like sim of G in the 1D case. I'd like to sort of give a similar kind of homological, homotopical construction of the symmetry algebra as a prefactorization, as a kind of model. I think this is a construction that's interesting, even just purely as a topologist, ignoring field theory. Okay. So here's a prefactorization algebra. Of symmetries. Given the time, today we're going to do the case, or do the one-dimensional, and then we'll study higher dimensional versions in later lectures. So, for simplicity, instead of dealing with the Lie group, I'm going to think about a discrete group. To emphasize that it's discrete, I'm going to call it D instead of G. So, a D be a discrete group. My favorite example is Z mod 2. Okay. So I should say that one-dimensional case means that M is going to be the real line. So we're going to put a prefactorization algebra on the real line determined by the group. So I'm going to call a fact a bundle of very beautiful facts from algebraic topology. Many of you have probably seen, but maybe not everyone. So associated to this discrete group, there's a topological space that I'll call B of D that's unique up to weak equivalence, weak homotopy equivalence. So I'm only going to sort of characterize it by its homotopy type. Characterized by the following facts. So it's going to be connected. Zeroth homotopy group is point. My one of BD is going to be the group D again. And all the higher homotopy groups are going to be zero. There's only got one interesting piece of sort of homotopical information. Now, this space ends up being a kind of moduli space. There's the best way to think about it is in terms of the following terms. So in a compact space Y, if I think about maps, the continuous maps from Y into BD, and then I look at its connected components, this is isomorphic to the principal D bundles, or if you want sort of covering spaces, appropriate set of covering spaces, so D bundles. Y, modulo isomorphism. Okay, so it's classifying D bundles as space.
And do you like want D to be discrete, or are you using this for?
D discrete, right?
No, I'm asking if
I do want D to be discrete for the purposes of what I'm gonna do next. Like, yeah, we'll think about Lie groups later and continuous things too.
basically the question is, does this like you can say the same thing?
Well, yeah, but this,
Yeah, no.
okay. So I want to point out that one consequence of this isomorphism is that it has a natural base. So there's always the trivial D bundle. So BD has a base point. Given by the trivial. There's always a preferred base point in this set. Okay. Another notation that people use is sometimes K D1 for Eilenberg instance. So for my favorite example, one model of BZ2 is RP infinity. Do you know at least one example? So I want to talk about a functor now. So there's a functor. Very analogous to what we've talked about already. That goes from opens in M, a closed set of opens in M, to topological spaces. Let's just say the real line. I'm doing M being a real line. If I have an open set U, it goes to what I'll call the space of compactly supported maps from U. What does that mean? Compactly supported means that if I have some map from gamma from U to BD, then the closure of, I take BD and I remove its base point, the closure of this pre-image is compact. So maybe it would help to draw a picture. So suppose that U is an interval, open interval, and I'm picking some gamma. Here's my picture of BD. So this interval is going to be broken up into pieces. So there's some base point here. Here's my base point. Well, if I think about this stuff away from the base point, well, let me actually draw in red all the things that go to the base point. So here's some agents. Then there's some subinterval, I1 and I2. And during the I1 period, you're allowed to wander away from the base point. So this is where gamma of I1. So you sit there for a while, you suddenly do something, you make a little loop, and then later I2 goes around, and then you sit there at the base point. Okay, those are the kinds of maps you're allowed. So if you unwind what this says,
Alright, do you mind raising that one that's on the bottom really quickly?
raising it,
I don't think that anyone back here can see it, like what's on that very
that's
bottom.
fine, I'm happy to raise it, it's like not a big deal. That's a
I
great
just
question.
want to see it, thank you.
So what this kind of argument shows is that if I think about this is an interval. And outside of some sort of finite periods of time, everything's sitting at the base point. So this is actually isomorphic to pointed maps or base maps from S1 into BD. I could, if you want, glue the two endpoints together. Okay. This is sometimes called denoted as the base loop space of BD. So notice that I naught in this case is exactly the same thing as pi naught of these based maps. So this is pi 1 of BD, which I've already told you is D. So in analogy with what we did before, I can imagine applying pi naught and going to the category set, a composite functor. I just told you the value on an interval is the set D. Fine. Sure. Determines, in fact, a pre-factorization algebra on R with values in set with the product. So let me just quickly sketch that. Let's just think about again. Two intervals U1 and U2 contained in some longer interval V. Here I'm thinking about compactly supported maps on U1 disjoint union U2 to BD. This is equivalent to compactly supported maps on U1 into BD across compactly supported maps to U2 on BD. Now, since everything has to go to the base point towards the ends of the interval, you can just extend by the base point in the rest. So there's a map from here, compactly supported maps on B. This map here is exactly concatenation of loops. Okay, it's concatenation of loops. So when you apply pi naught to it, you're seeing the multiplication. So it's not just this, but it completely encodes. This encodes the group multiplication. So we have a prefactorization algebra that knows D. I mention one variant here I think is useful to see. We could change the functor here And use a more interesting functor. We could take singular chains with coefficients in some commutative ring. So that would go to chain complexes over R. And in that case, you again get a prefactorization algebra, but now with values in chains, tensoring over R. And in this case, what I want to point out is chains on the base loops of BD with coefficients in R. So this is coming from an interval, right? This is quasi-isomorphic to chains on this discrete group, which is a collection of points with values in R. And this is quasi-isomorphic to just R. This is the free R module on the set B. And similarly to the argument over here, we got the group structure on D. You can check that if you have two intervals going into a bigger thing, you get the multiplication. So this composite, this encodes, or if you want, recovers the group ring. D with coefficients in R. Okay. So the upshot of all this was that prefactorization algebras are this nice place where we can, among other things, actually get things like groups or group rings constructed in this way, very similar to the way we do it in field theory, where we pass through some big category, kind of amorphous category, and then maybe linearize it. So next time, we'll build on this and we'll discuss a context where this prefactorization stuff works really nicely in field theory to capture moment maps and quantum moment maps. Okay, it's the setting of perturbative QFT and the BV formalism. Then we'll get rid of the pre. We'll talk about what a factorization algebra is and how it fits in with that story. If we have time, we'll talk a little bit about non-perturbative aspects of QFT.
Questions, comments?
So this factorization algebra encoding the and it acts on one.
Hoping to find some way of saying that isn't too fancy. So I'm kind of working on it. Yeah, to fit in the lectures, we'll see.
The other questions? Let's take Owen again. See you all tomorrow morning. Usual time.